when we go from an algorithm to a program, we have to be a little bit more careful, because now this algorithm really has to be encapsulated. It has to be encapsulated so that we can have a function that we can name, and then we have formal parameters, and then we can call that function with actual parameters. So let's just call it matrix multiplication. And obviously I need A, B, and C. And I also need n as a parameter. So that will do the trick. And now if we take this as our program, then that's sort of what we would expect. Now, if I want to actually call this function, I could do something like this. X, Y, and Z, so X and Y are the X, Y, and Z are the three matrices, and 10 is n, so these are 10 by 10 matrices, so each of them has 100 elements. And now, of course, the important aspect is that I could then call this function again. For instance, with Z, X, and Y, which would then take the Z that I calculated in the first call and multiply it with the X and assign the result to Y. So clearly, what is important here is that I'm using this function to get several calls implemented. If I really only wanted to do one, then I could just inline expansion, and that would be no problem. But if I have many different calls to that function, then obviously I want to have a function that I can name, in this case matrix multiplication, and then I have actual parameters and formal parameters. So A and B and C would be the formal parameters, as well as n, but the n is not really that interesting. These are formal parameters. And then the actual parameters here are x, y, z in the first case, and z, x, y in the second case. And so what is really then important to understand is these are actual parameters. And so what is important to understand is how these formal parameters are tied up with the actual parameters. Obviously, the actual parameters are the things that we actually want to solve for. The formal parameters are really just a template that allows us to formulate, in this particular case, the body of the function, matrix multiplication. So I, j, and k, these are variables, runtime variables. N is a parameter, and A, B, and C are formal parameters. And then we want to work with those in order to do, to actually get a result. And so what we need to do then is to define quite carefully, actually, how these two concepts, the actual parameters and the formal parameters, correspond to each other. And there are really three different ways, only two of which I'm going to look at. they're called by value, called by reference, and called by name. Now, the third one is really not that important for a number of practical reasons. The most important one is that most programming languages don't implement it. So if you can't invoke it, it probably doesn't make a whole lot of sense to talk about it. It is basically a macro. But the other two, value and reference, are present in different programming languages, not necessarily both of them, but depending on how it's implemented, one or the other, or both. And so from a complexity point of view, we really have to understand how all that hangs together. And so let's look at this connection. We have actual parameters and we have formal parameters. And in the case of value, the first step is each actual parameter must have a value. Number two, each formal parameter must correspond to a memory location. Now, this is loosely formulated, obviously, in the case of matrix multiplication. If your formal parameter, in this case, for instance, A, is a matrix, you actually need an n by n matrix. So this would be in squared memory locations rather than one, but you see what I mean. Number three, for each actual parameter, its value is copied into the corresponding memory location. So what we have here is we have an actual parameter which corresponds to a formal parameter. Now, the actual parameter has to have a value, the formal parameter has to have a memory location, and then we're going to copy that value into that memory location. And the rest is quite simple. Execute the body of the function as if the formal parameters are local variables. So that means go back to this algorithm, which we now want to make into a function. And in order to achieve that, we have to make some decisions about what it is that we want to do with those parameters. In particular, how do we tie the formal parameters to the actual parameters? So if we look at this first function call, matrix multiplication x, y, z 10, then if a, b, and c, if x, y, and z are passed to a, b, and c by value, then number one, x, y, and z have to have values. So that means there would be 100 values in X, 100 in Y, and 100 in Z. And then when we call matrix multiplication for X, Y, and Z, we have to allocate 100 elements for A, 100 memory locations for B, and 100 memory locations for C, because that's what these matrices X, Y, and Z are. And now, having allocated A, B, and C as 10 by 10 matrices, we then take the values that are in X and copy them into A. We take the values that are in Y and copy them into B, and we take the values that are in Z and copy them into C. And then we run through that body. And so that means we are calculating the values, and it should be fairly obvious that in the end, when we finish with the I, J, and K loop, with those three nested loops, we will have in C the product of A and B, which of course would be the product of X and Y. And now what happens? What happens if I execute a function and I have a local variable? What happens to that local variable when I return from that function?
It gets discarded, no?
It gets discarded. So after I have carefully calculated the matrix multiplication of X and Y in the matrix C, I'm going to throw it away. So obviously it is not going to be in Z, and that means I really have nothing that I can show in the calling program where I call matrix multiplication X, Y, Z, and 10. And so clearly call by value is not going to do me any good, because yes, I get the value, I get what I wanted to do in C. I get the product of X and Y, but then I don't have any way of bringing it back into the calling program. So the Z will still have whatever there was before in Z, and the C that I carefully calculated in times n to the third is going to be thrown away. So that is probably not a particularly attractive proposition, because I'm not getting anything. So we have to look at the other possibility. What happens if we do call by reference?
Quick question, Dr. Lois.
Yes.
If we were evaluating aside from the incorrectness of the algorithm, since we don't get the result in Z that we want, when evaluating the algorithm, would we treat copies and the assignments in the algorithm as equal operations? Because it would be 3n squared plus O of n cubed.
You're getting ahead of me. Hold on. Yes, we're coming back to that.
Okay, sorry about that.
Yes, absolutely. There is more to it than just that it is not correct. We'll also have to look at what is the cost of doing these things. Okay, so hold on. We'll get to complexity in much more detail than you probably care for. All right. So reference. What happens in the reference? Well, number one, each actual parameter must correspond to a memory location. Any use of a formal parameter uses the corresponding actual parameter. And then execute the body. So in this particular case, if we do call by reference, then if we go to this algorithm, and now making it a program as a function by doing A, B, and C by reference, we go in there, so the actual parameters are X, Y, and Z. They better be matrices, n by n matrices. That would be reasonable to expect. Otherwise, it doesn't make any sense to call matrix multiplication X, Y, and Z 10. And now that means that X and A are tied to each other. So whenever we are making a reference to A, we are really making a reference to X. So if AIK is used in the body of the function, then effectively, if these are passed by reference, we are referring to X, Y, and K. Similarly, BKJ is YKJ, and CIJ is ZIJ, because C and Z correspond to each other, and B and Y correspond to each other, and A and X correspond to each other. And similarly now for the second call, the A and the Z correspond to each other, and the B and the X correspond to each other, and the C and the Y correspond to each other. So that is exactly the way it works. It obviously requires no additional memory locations, because the memory locations for the formal parameters are already provided by the memory locations of the actual parameters. And so everything seems to be perfectly good. Seems to be. Here is where everything goes to hell. I am going to take the product of two matrices X, and I'm going to assign that to X again. I basically square. And so let's look at what happens if X is 1, 2, 3, 4. Well, I'm going to go back to the function, because that clearly is you don't believe me if I just throw it at you, so I have to carry it out. Where are we? Yeah. I have to carry this out quite carefully. So we have 1, 2, 3, 4. This is our matrix, and what I'm going to do is I'm going to write it down so that I'm not just erasing, I'm basically crossing it out and write the new values down so you actually see all the history. So we're now talking about call by reference, which means this matrix has 4 names. It has name X, obviously, It has the name A, has the name B, and it has the name C. Because if you go back to this function call, this corresponds to A, this corresponds to B, this corresponds to C. So all four names refer to this matrix. And now let's go laboriously, slowly through, because you don't really quite believe the result unless I do that carefully. So we have n is equal to 2. So we have I is equal to 1, j is equal to 1. So the first thing I do is C11 is 0. So C11 is x11, which means this becomes 0. Okay? And then I do k is equal to 1. So I have C11, which is of course x11, which is 0, plus A11, k is 1. So this is x11, so this is 0. And then I have B11, and so this is 0. So this is 0 times 0, and I add that to 0, so I get again 0. And then I get k is equal to 2, so I do C11, we're still I and j is equal to 1. And so this is C11, which is x11, which is 0. So this is 0, plus A12, which is x12, which is 2. And B21, which is x21, which is 3. So this is 2 times 3. So that is 6 plus 0 is 6. So that is I is equal to 1 and j is equal to 1. Then we do I is equal to 1 and j is equal to 2. C12, which is x12,
Professor, can I take this moment to ask where in your programmer's companion is
question? I can't hear you.
Can I take this time to ask where in the programmer's companion is this?
Say that again.
Where is this in the book?
Oh, this is on page 151 through 154. This is section 6.4. Okay, so we're done with I is equal to 1 and j is equal to 1. Now we do I is equal to 1 and j is equal to 2. So that gives us C12, which is x12, which is this. So that becomes 0. And then we go k is equal to 1. So C12, which is x12, this is 0. And then we have A11, which is 6, and B12, which is 0. So this is 6 times 0 is 0. So 0 plus 0 is 0. And then we have k is equal to 2. This is still 0, 2, 1. And 1, 2. C12 is x12. And then we have A12, which is 0. And so this is 0. And so the result is 0. Then we do I is equal to 2 and j is equal to 1. So C21, which is x21, is 0. Then k is equal to 1. This C21, which is x21, is 0, plus A12, to 1, which of course is 0. So this is 0, whatever b is immaterial. This is going to be 0, and 0 plus 0 is 0. And then we have k is equal to 2, so we still have c to 1, which is x to 1, which is 0, plus a to 2 times b to 1. b to 1 is 0, so a to 2 is 4, but 4 times 0 is 0, so this is 0 again. So that means that this is 0. And finally we get to I equals 2 and j is equal to 2. So first c to 2 is 0, which is x to 2 is 0. So we get 0 here. And then we have k is equal to 1, c to 2, which is x to 2, which is 0, plus a to 1, which is x to 1, which is 0. So this is, that product is 0, so 0 plus 0 is 0. And finally, k is equal to 2, c to 2, which is x to 2, which is 0, plus a to 2, which is 0, so this is 0. So the result of that is that we get 6000 from our algorithm. So 6000. That would be the result that we obtained. Now, let's find out what it is that we really ought to be getting. 1, 2, 3, 4 times 1, 2, 3, 4. So 1 times 1 is 1, plus 2 times 3 is 6, so that is 7. 1 times 2 is 2, plus 2 times 4 is 8, that's 10. 3 times 1 is 3, plus 4 times 3 is 12, 15. And finally, 3 times 2 is 6, plus 4 times 4 is 16, 22. This is what we should be getting. 7, 10, 15, 22. What we are getting from our seemingly correct program is 6000. Obviously, signally wrong. This program is wrong. Just dead wrong. So, what is it that actually screwed us up? Well, this ties back to our first theory question in assignment 2. The question there, if you recall, was we have two data structures, and how do we find out whether they have anything in common? Well, that question of having anything in common is, of course, very starkly illustrated by this particular call. They have everything in common. X, X, X for A, B, and C. And so while it makes sense from a mathematical point of view, we want to square X and assign the result to X again. This program, as we have implemented it with passing the parameters by reference for A, B, and C, is simply dead wrong. So that, of course, is because this C has stuff in common with A and with B. So what really happens here is when we do that assignment of 0 to C, Cij is 0, we are not just setting C to 0, we're also setting A and B to 0 in the appropriate places, which is, of course, very inappropriate, because we don't really want to change A and B. We only want to assign a value to C, but inasmuch as all of these values, these memory locations, have 4 names, X, A, B, and C, if I mess with one, in this case C, I am messing with all of them, and in particular with A and B. So what that really means is, if there is an overlap between, say, C and A, or between C and B, then this program with A, B, and C passed by reference is possibly wrong. And so that's, of course, the background to that question, because if you could test what is going to screw you up, namely that there are elements in common, then you have to be careful. If you, on the other hand, know that there is nothing in common, then you can do A, B, and C by reference. But if that's not true, then this example very starkly illustrates that you are not going to get any correct result. Now, I would argue that most of you probably didn't have any inkling that this is wrong. And the reason why it is wrong is because of the way in which the parameters are passed. So let's see what we can do to salvage the situation. Well, what if we want to keep the program that we have, this program, with A, B, and C, and N? Now, I've ignored N because N is really not that important. You can do it however you want. You can do it by value. N is not going to be changed. N is not going to have any influence on anything. So whatever you do, N is fine. You can use it by reference. You can use it by value. It doesn't make any difference. But it does make a difference what you do with A, B, and C. And so if we want to maintain this program, then the question is, what do we have to do? Well, we have to do A and B by value and C by reference. If we do that, then what happens is we're going to, in this infamous example, XXX, what we do is we copy one X, well, X into A. So in that case, everything that is in X is now copied into A. Obviously, A, for that purpose, needs to have allocated a matrix, an n by n matrix. But once we have that, we can then copy one X into A, and then we can copy the X again into B. And that's what we need to do, A and B. If you look at the definition, each actual parameter must have a value, so that is clearly given. If we have X and we want to square it, each formal parameter must correspond to a memory location, so that stipulates that for A and for B, since they are passed by value, we have to have n by n matrices, one for A and one for B. And then for each actual parameter, its value is copied into the corresponding memory location. So the values of X are going to be copied into A. The values of B are going to be copied into, the values of X are going to be copied into A. And then the values of X are again copied into B. So at that point we have two local variables, both of which contain x, if this is the function call. And then we carry out this. And now, obviously, whenever we mess with C, which is by reference, which basically messes with x, because this is that x that corresponds to C, and that C then gets changed. So it is the x that is being changed, but that has no bearing on what we have in A and in what we have in B, because they stored, they saved, put on ice all the values of x, and any change of C, which means a change to x, is not going to affect any of the values in A and B. So when we now do the accumulator here with the A times B terms, then those are not going to be affected. The A is going to be the A and not the X, and the B is going to be the B and not the X. And so when that happens, nothing will be changed because of that assignment of 0 to C, which is, of course, a change of X. And so that means the algorithm that was, of course, correct, when encapsulated using A and B by value and C by reference, and of course, for completeness sake, N probably also by value, because that really isn't that important. That means this is now correct. So MatMult is correct. Okay, so that is step one, but there is a little bit of a problem. We do have to do the complexity analysis, which comes back to the question that one of you asked before. When we do this copying business, for each actual parameter, its value is copied into the corresponding memory location. Well, in this particular case, A and B are matrices, and they are copied. They get copied the values. Well, in this particular case, mult x, y, and z, the values of x are going to be copied into A, the values of y are copied into B, and C, of course, is a reference, so whenever we have a reference to C, it will mess with whatever is Z. That means, of course, two things. We have to look at space, and we have to look at time. Well, space is, of course, fairly obvious. We have to allocate two n by n matrices. Each formal parameter must correspond to a memory location. That means we need n squared times 2, one for A and one for B, space, in addition to whatever else is there, which is very little, because the only other thing are those three variables, I, j, and k. So that is cheap. There are three simple variables, I, j, and k, but what is not cheap is the space that is required to accommodate the mechanism of passing A and B by value, because that mechanism requires that A and B be associated with n by n matrices, and that gives rise to the 2n squared space requirement. Now for time, well, if you look at this algorithm, then obviously you have here n squared Cij, that occurs n squared times. And then you have this plus and this times, which occur in cubed times. So if you just look at this, you have obviously n squared plus 2n cubed. That comes directly from the algorithm. But what this does not account yet for is, of course, that when A and B were given their own memory locations, which is where the n squared, 2n squared space comes from, we also have to copy those values into the corresponding memory locations, which means that in order to do that, we also need n squared times 2 time. One for A and one for B, and both of them are of size n squared, and so that's 2n squared plus whatever we expect for the algorithm in and by itself, n squared plus 2n to the third. So that means we now are really looking at a significant increase. We went from a constant amount of space to essentially 2n squared space because of the requirements that are imposed by call by value. But, well, it is at least correct. It may take a little bit longer, but it is correct. If we go with this, with all three parameters called by reference, which is faster, because in that case we don't need any additional space, and we only need the n squared plus 2n to the third time. We don't need those 2n squared for space and 2n squared time, but of course it isn't correct, which if you want to have something fast, well, just print out 0. It may be wrong, but it is very fast, but that's obviously not going to be useful. Now, we're not done yet. Having done this analysis, it behooves us to actually re-examine that code again. And it turns out that we can improve things. We can come up with a new version. So this is the primed version, A, B, C, and N. And we do exactly the same thing, except we are setting up first a new array D, which is a local array. And then we do I from 1 to n, j from 1 to n, and then we do d ij. So effectively, the C in the original algorithm is now going to be replaced by D, and then we have the K from 1 to n, and there is D ij is Dij plus Aik times Bkj. So at this point, what we have is that the product of A and B resides in D, which is a local variable. And now we're going to do I from 1 to n, j from 1 to n, Cij is Dij. So at this point, we basically now copy what is in D, in the local variable D, into C. And this we can do with A, B, and C by reference. because this D has nothing in common with A, B, or C. And so the fact that we're messing with D, Dij is 0, has absolutely no bearing on A, B, C. So even if I do this evil call, matrix multiplication x, y, x, and 2, well, if I do matrix multiplication prime x, then what I'm going to get is A and B are going to be x, but D is not. So I'm correctly calculating D, which is the product of whatever A and B correspond to, in this particular case, in case of that evil call, x and x. So D then contains x squared. And only after I have carried out all that, then I am going to copy the content of that array D into the array C. And that, of course, now gives me exactly what I want, because now the product of A and B does, in fact, correctly reside in C. And at that point, if we do A, B, and C by reference, then we're not incurring any penalty. So when we do the complexity, the space, well, what is the space? Because of the reference A, B, and C, we get nothing. Now, we do need to allocate D. That requires n squared space. And then we have a I, j, and k, so this is plus 3. So that means we basically have cut the required space from matmult to matmult prime in half. 2n squared plus 3 versus n squared plus 3. And the same thing holds for time, because, well, there is, of course, the actual algorithm, which is n squared plus 2n to the third. And the additional time that is required is, of course, the time to do that that copying of D into C. And so this is n squared. So what that really then means is that altogether you are looking at a significant reduction. Certainly in this case of space, you basically cut it in half, from 2n squared plus 3 to n squared plus 3. And the additional time that is required over and above what the algorithm requires. The algorithm requires, of course, n squared plus 2n to the third. That's where you would do the complexity of the algorithm. But then when that algorithm is going to be encapsulated into a function, additional work has to be done. And that is a crucial observation. The algorithm in and by itself can be much less time-consuming than the additional work that has to be done. So in this case, what is the space complexity of the algorithm is 3, and what the time complexity of the algorithm is n squared plus 2n to the third. But the additional work that the actual encapsulation requires, if you just stick to matrix multiplication, the original version, then the additional space is 2n squared, additional time is 2n squared. If you are slightly more sophisticated and you do the analysis more carefully, you can do matrix multiplication prime, which will cut the additional requirement by half. N squared space versus 2n squared space, n squared time versus 2n squared additional time. It looks more complicated. It seems that you do more, but it is important to understand that ultimately, in order to end up with a correct program, with a correct function, you have to bite the bullet and decide how you're going to pass the parameters. And depending on that, you may end up with a much greater time complexity and a much greater space complexity than what you originally envisioned. If you stick to the original formulation of the algorithm, your additional space is 2n squared and your additional time is 2n squared. If you modify it, then you can cut that in half, but it is still a significant increase over what the algorithm would suggest is needed. The algorithm would suggest you need order of 1 space and n squared plus 2n to the third time. You actually need at least n squared more, both space and time. So what is important here is that you understand that when you go to a function, you are going to incur additional costs that we tend to completely ignore and put aside when we look just at the algorithm. The algorithm, as I said, requires constant amount of space and n squared plus 2n to the third time. Any way you slice it, if you encapsulate that into a function, is going to require more than that. Require a lot more space and a good deal more in time. Now, as I said, if you can determine that these elements, so if you knew that C has nothing in common with B and C has nothing in common with A, then of course you could in fact go straight with the algorithm as it is with call by reference, which would require space 1, 2, 3, simple variables, one for I, one for j, and one for k, and you would not need any additional space because of passing parameters. But if you can't guarantee that, then you have to bite the bullet and do either the A and B by value, or you're going to go with the other version, the matrix multiplication prime, which does the local variable d and therefore cuts the additional time and space complexities by half, but it is still significant. So that means that effectively, if you could determine that C has nothing in common with A and C has nothing in common with B, then you could pass A, B, and C by reference, and you could use this as it is without any further ado. But if you can't guarantee that, then you have to take either A and B by value, or you take this new algorithm, and then you can do A and B and C by reference. Any questions about that?
Professor, I have a question about it. In terms of when is it that we would actually be able to figure this type of problem out? So, like, at what point do we have to wonder whether this would be better? Because would it have to be in a matrix multiplication only, or does this type of problem come up in any other type of situation?
It could come up in any type of situation. I'm using this because you all think you are thoroughly familiar with matrix multiplication. And as you know, I am somewhat devious in showing you that perhaps you don't quite understand it. And I would suggest to you that most of you would probably have gone with this by reference without further ado, and so you were probably quite horrified when I demonstrated that that program does not work. So what that really means is that we have certain implicit assumptions that may not necessarily be satisfied. In this particular case, of course, the implicit assumption was that these A, B, and C matrices are completely independent of each other, which of course may be true, but it may not be true. And if you indulge me and accept this as a valid function call, which I would suggest you have to, because why should this not be permitted, then you can see that the direct implication using call by reference for A, B, and C for this program, now not just algorithm, but a program, a function, is wrong. And so what I'm really suggesting is whenever you program something, you actually have to think about what happens if somebody devious like me comes up with something that screws things up by having this type of function call. So actually, I would argue that that is something that you all have to consider when you design your programs. The fundamental difficulty, of course, is, in this particular case, that everybody thought they knew what matrix multiplication is all about, and everybody accepted this type of algorithm as perfectly correct, and it is, but it is not correct once you start encapsulating it as a function, because now you actually have to think about how do we pass those parameters, and once you get into that, then things get much more complicated. Does that answer your question?
Yes, sir. Is there any place where we can reference this for like a real life problem? I know that whenever we first were introduced to this, you mentioned the moon landing being one of the problems where something like this might have happened.
I didn't mention the moon landing, but there's certainly a number of issues that arose over the many years that we've had software that are where algorithms were wrongly implemented in software. And so, I would argue that it is probably very difficult to come up with something less fundamental than matrix multiplication. This is something that we sort of routinely do, and if we do it badly, and badly would be passing A, B, and C as by reference without considering that there could be bad things like this, then you may end up with something that is entirely wrong. I mean, clearly this 6000 is very far from 7, 10, 15, 22. And given that matrix multiplication is a very, very common algorithm, I would argue that that is something that really should be considered quite carefully. I'll give you another example. Okay? And that is binary search. Another one that you think you know. So binary search, you have an array A, you have an X that you're looking for, you have low and high. Okay, that's basically what binary search is all about. And X, low and high are probably going to be by value. Why? Because value is safe. Value is safer than reference. Why? Because in reference, if you screw something up, if you change something, for instance here, the value, if its name, I'm sorry, if its value, then you copy basically things into what amounts to a sandbox. Whatever is inside that sandbox, nothing can get out if it is by value, because you can mess with it in the sandbox, but it will never get out, because in order to get out, there has to be reference. So reference is actually much more dangerous than value. So if you have a choice, and in this case, it doesn't really make much difference. It costs you a little bit more. You have to do the copying business, but this is not that often. So effectively, this is going to be safe. A, on the other hand, is another question. So what happens if we if we call A by value? Now, in this particular case, it is clear that you're not going to mess things up as far as correctness is concerned. The binary search algorithm will work correctly if you pass the array by value. However, let's look at the complexity. Binary search, of course, the big attraction of binary search is that if we have a binary search of a x1 n in elements, well, then we need this time complexity is log of n, log base 2 of n. But what happens if we pass A by value?
We lose the log n time. That's the whole reason that we use binary search tree, because then it becomes...
Right. You basically louse everything up, because the time it takes to copy. So if you do binary search for some x, a and 1 and n, well, the actual parameter is x. We set up, call by value, we set up an array, a vector A of size n, and then we copy x into that vector A. Well, that takes order of n time. And so we have n for the copying plus log base 2 of n, which is, of course, order of n. That is exponentially worse than what binary search is expected to give us. This is exponentially worse than that. So actually, if we implement binary search with that parameter, the array being passed by value, this is worse than any linear search, because this is going to be slower than n. Whereas linear search will always be no more than n. So that is an example where you end up with something that is correct in contrast to the matrix multiplication algorithm. But it still is horrible, because it basically now replaces an log n process with one that is n, which is exponentially slower than what you would expect, because n is 2 to the log n. So this is 2 to what it is that you would expect. And so from that point of view, you really have a situation that is extremely undesirable. And the only way in which you can understand what is happening here is by making a careful analysis of how the parameters are passed. This binary search algorithm is log base 2 of n. And if you just say, all right, we're passing this array by value, then who is the wiser? Except the resulting solution that uses that stupidly implemented binary search algorithm is going to be terribly slow, because it isn't doing log n, it's doing n. And so these kinds of things are important to be considered, because if you don't pay attention to that, you're going to end up with very subpar implementations. So the actual implementation of an algorithm is crucially dependent on a careful analysis of what has to be done in order to pass the parameters properly. If you don't do that, you can end up with a wrong algorithm, a wrong program, as in the case of our discussion of the matrix multiplication, or you can end up with something that is horrifically slower than what you expect, as this example binary search indicates. Any questions? About this or anything else?
I got here a little late, but did we get the assignment 2 graded yet?
No. What do you mean? We will try to return that by the 13th, Monday.
Dr. Elias?
Yes.
I never received the regrade back of the first test.
Send me an email and I'll pass it on to the graders.
All right, thank you.
Okay. Any other questions? All right. Then we will talk to each other on Monday again. Have a good evening. Bye-bye.